Let's talk about the impact of biodiesel. So first of all, what exactly is biodiesel? So you'll remember that most diesel obviously is derived from crude oil sources. So we go out, we explore, we drill, we pump this stuff out of the ground, then we take it to a refinery, we refine it into different products. Some of those become lubricants, some of them become diesel, right? Well, obviously, biodiesel doesn't really work the same way. We start off with some kind of bioproduct, some kind of living organism, typically a plant, right? So palm plantations are where a lot of biodiesel is derived from. Sunflower seeds is another really good example. We basically harvest these crops and then we use the seeds, right? And we use the oil from the seeds. So just like you press and you get olive oil, you can press a lot of these other seeds and nuts in order to get an oil, right? And with a little bit of refining, we can then basically turn them into biodiesel. Now, sometimes you'll hear it called FAME or FAME, which stands for a fatty acid methyl ester. Right, that's effectively what biodiesel is. So what exactly is that? All right, so let's take the different components of the name and sort of break it down. Let's say I have a straight carbon chain. Now, of course, each of these carbons has a couple of adjoining hydrogens on it. I don't show those for simplicity's sake. So let's just say that we have a straight hydrocarbon chain. Well, if I have an acid functional group on the end, then right, that is what we typically call a fatty acid when it comes to organisms, right? So we have lots of fats in us, whether they're fatty acids or triglycerides. So do plants, right? They generate these fatty acids in their seeds or nuts. All right, so we have an acid functional group. Now, what's great about some of these plant varieties is that they happen to generate fatty acids which are just the right size for diesel. So if you'll remember, right, diesel comes out of the ground and it's just crude oil, and the exercise of refining is to kind of separate these out into different fractions. So if we have gases, methane only has one carbon, but methane, propane, butane, you start to increase the number of carbons. And as you increase the number of carbons, then the end product gets thicker or more viscous. So then if it's about 8 carbons long, that's typically, gasoline or petrol. 12 carbons long is approximately kerosene, and 16 carbons long is approximately diesel. Well, as it happens with a lot of these bio-derived products, what we get is, something that looks like this. This, in particular, is one of a handful of vegetable fatty acids, and the one that I've got on screen happens to have 18 carbons, which corresponds to something called stearic acid. Now, all of these different ones that I've got up on screen have different carbon chain lengths. 14, 16, and 18 is very, very typical. So, palmitic acid, which has 16 carbons, the clue is in the name, right? Palmitic is because it's very common in palm oil. Now, what is the difference between stearic, oleic, and linoleic acid? Because they all have 18 carbons in their chain. Well, it's got to do with what we call saturation. So, what I'm showing on screen here with a completely straight carbon chain is what we call a saturated fatty acid. So in your diet, you would hear it called a saturated fat. And that effectively means that there are no double bonds anywhere along the carbon chain. When we get to oleic acid, what it means is that there is a double bond somewhere in the chain. It doesn't really matter where in the chain it is, but somewhere along the chain, we have a single double bond. That actually affects the shape of the molecule too, because double bonds tend to sort of bend the molecule. So now, because we have a single double carbon bond in the link, we would call this a monounsaturated fatty acid. So it's unsaturated because it has a double bond, and it's monounsaturated because there is a single double bond. If we were to have a second double bond in the chain, then we would call it a polyunsaturated fatty acid. And this, in this instance, we would call it linoleic acid. So it's 18 carbons long, but it has 2 double bonds in it. And the position of those double bonds can vary. Now, what's important about saturation? Why are double bonds undesirable? Well, if you remember back to our API base oil groups for lubricants, one of the things that defines group 1, 2, and 3 mineral oils is the degree of saturation. And the more saturated the end product is, the higher quality the product is. Now, why is that? It's because in a double bond, the second bond is easier to break than a single bond, so it's less oxidatively stable. So molecules that are unsaturated tend to be less oxidatively stable. Now, that's a little bit of a problem when it comes to biodiesels. And the reason for that is because if you look at the composition of some very, very common vegetable oils, what you'll see is that, for the most part, they are unsaturated molecules. So what I'm showing here is, if you remember, blue and green are palmitic and stearic acids, so 16 and 18 carbon long fatty acids, but those are the saturated ones. The unsaturated are represented by the bright red and the bright purple, which are the oleic and linoleic acids. So what you can see is, especially the sunflower oils, but even the palm oils, are more than half unsaturated, and so that makes them oxidatively unstable. So if we go back to this idea, we're not quite complete yet. We've explained fatty acid, and we've explained saturated and unsaturated. So what's the methyl ester part? Well, basically, in order to create biodiesel, we take these fatty acids and we react them with methanol, right? So methanol is the methyl part of the name, and it undergoes a reaction which we call an esterification process. So basically, we are creating an ester, right? So if we have an acid and an alcohol, so we had linoleic acid plus methanol, acid plus alcohol makes an ester plus water. And so that's the esterification reaction. And so that's how we get to fatty acid methyl ester. So that's effectively what the biodiesel molecules are. Now, when they're marketed, you'll typically see them called something like, B5 biodiesel, or maybe it's B10 or B20. So what does that number refer to? So B20 means that the diesel that you're putting in your engine is 20% biodiesel, and therefore, by extension, it's 80% crude oil derived, right? So it's 20% natural, 80% crude or mineral oil, if you want to call it that. Now, around the world, there are different rules and regulations about the biodiesel content, right? So let's say, for example, in kind of my backyard, in my part of the world, Indonesia brought a mandate in 2020 that all the diesel across the country be B30, right, which is 30% biodiesel or plant derived. Malaysia has a view this year to bringing about B20, so 20% biodiesel mix. Now, there are a couple of drivers behind that. One, these countries tend to import a lot of diesel, and so they want to rely less, right? And as it happens, they have huge palm plantations, right? So they have a rich plant source to be able to derive biodiesel from. If you go to somewhere like Australia, it varies by jurisdiction. So in my state of New South Wales, I think the rule is that 2% of the volume which is sold by fuel distributors needs to be biodiesel, right? And it varies state by state. The same goes for the US. I think the mandates vary by state, and that's true of places all across the world. But the fundamental kind of underpinning trend is that the volume of biodiesel continues to increase year on year, and it's starting to grow its market share as people look for kind of renewable fuel sources. Now, we could spend a whole nother hour talking about the environmental costs versus benefits of biodiesel. Obviously, if you're growing monoculture plantations, that can be bad for the environment. We're not going to get into it here. But what I do want to focus on is how it affects the engine and the lubricant system. So when you have an engine, the one thing that we cannot avoid as much as we would love to is some degree of blow-by that occurs past the rings. And so some measure of kind of blow-by and fuel dilution of the lubricant is going to be unavoidable. So what is kind of different about biodiesel? Well, first of all, because it's so unsaturated, it's less oxidatively stable. So we tend to get, as it mixes in with the lubricant, it breaks down. Typically oxidation will lead to things like viscosity increases and more deposits. It's also less hydrolytically stable. Being an ester, when it comes into contact with water, right, it breaks down back into an acid, right? So we are creating acids all the time, and then we can run into problems with corrosion, and particularly in the crankcase, we'd be concerned about the crankcase bearings. So that hydrolytic stability can really be a problem in engines because remember, water is also a byproduct of combustion, right? It's unavoidable that water will get into the crankcase. So the combination of water plus a bio-derived ester means that you're going to be producing acids. There is also some evidence that there is a negative interaction that happens with certain types of viscosity modifiers, and you can run into some low temperature pumpability issues. This seems to differ depending on the type of viscosity modifier, but without much information about the formulations of some of the diesel engine oils, it's very difficult to predict when this will happen. There is also some evidence that it can affect the seal swell of different types of materials. The evidence seems to be that for the most part it's okay, but in nitrile rubber and nylon seals it can have an effect on hardness and the degree to which these materials swell. And ultimately, when you put all this together, you end up with shorter oil drain intervals. So that's the major impact on the lubricant. On top of that, we're also increasing fuel consumption because the energy density of biodiesel is less than crude oil derived diesel, right? So although we're theoretically going from renewable sources, we're actually increasing the amount that we have to burn in order to power our engine. One of the other interesting impacts is that biodiesel doesn't volatilize the way that petroleum diesel does. So of course, with diesel, typically it's direct injection. So we're spraying effectively a fuel mist into the combustion chamber, and the whole point of the injector is it's trying to atomize the fuel. Well, if you compare what biodiesel looks like versus petroleum diesel, it tends to clump up a little bit more. It's not as evenly distributed. So what does that mean for our lubricant? Well, when we get less atomization of the fuel, that means that in local areas, we would say that it is fuel rich, right? And so we're entering a rich burn environment. When that happens, we typically have more incomplete combustion, and the product of incomplete combustion is soot. So generally, when we're burning a biodiesel, we end up with more soot in the crankcase, right? And soot obviously leads to increases in oil viscosity because of the loading of solids. And it can also start to wear the engine components as well, because when soot agglomerates, it becomes abrasive. So that's another negative consequence of the use of biodiesels in engines. Again, just to kind of belabor the point a little bit, but the hydrolysis reaction is basically the reversal of the esterification reaction. So when these esters come into contact with water, we are creating carboxylic acids as well as alcohols. Now, there is obviously some regulation that has sprung out about this. So the US and Europe have standards around biodiesel. In the US, you'll see it as ASTM D6751. And in Europe, it's EN 14214, right? That really kind of just sets the standard for what biodiesel has to be. But you really need to look at the engine manufacturers to see, did they design the engines with biodiesel in mind? Or if they didn't design it specifically with biodiesel in mind, have they since tested the use of biodiesel in their engines to ensure that it's not going to cause a lot of damage? Now, this isn't by any means an exhaustive list. This is just what I could find. Let's say the information may have been updated since you see this, since this video was published. So always make sure that you are going back to the manufacturer documentation to ensure that you have the most up-to-date information. But here what you can see is that effectively for most of the manufacturers, they are defining that concentrations up to 5% of biodiesel are generally okay. Some of them go up to 20% is okay. And then some say, well, you really need to maybe check. So as an example, if you look at the Scania list, it says, B5 is okay. If you want to go above that, you can, but you have to shorten your oil drain intervals. And then most of them will also say that the actual biodiesel that you're using must meet either the ASTM or the EN spec, right? So that's a really important thing. Now, one thing that we should take away from this is remember that Indonesia had mandated B30 diesel be used. And that kind of goes against what most of the engine manufacturers have really approved for use in their engines. So that's going to be a really interesting clash to see what happens in the Indonesian market over the long term. What does the performance of their engines do when running on this B30? So that's been a very quick primer on biodiesel, as well as some of the downsides to using it. Obviously, I'm not saying that you should never use biodiesel, but just be cautious about some of the negative consequences and be on the lookout for it, especially in your oil analysis.